it is going, the way I've drawn it, in that direction. So I could create a unit vector in that direction and just call it A hat. A hat being the direction of vector A. The magnitude is A. So my vector A hat, or sorry, my vector A is just the magnitude of A times A hat. Or if I need to define a unit vector more formally, any unit vector is equal to a vector in that direction divided by the magnitude of that vector. So given that, my R here is just the magnitude of R, the distance between what's creating the magnetic field and the point in question, times R hat. And so if we make that substitution, one of my R's cancels out, and so my second form of this mu naught over 4 pi dq v cross R hat over R squared. In terms of actual use, I think the first form works better than the second form, but you know, whatever way your mind is working at the moment, you need to use it. Any questions before I do the third form? Okay, let's do the third form. Velocity. What is the velocity? How is it defined? What is the meaning of velocity? Because people avoid eye contact.
Distance over time or something else?
That would be speed.
Distance over time in a specific direction.
Okay, or displacement over time. Or dx dt, it's the first derivative of position. So my velocity there, I can just substitute that in for it. So I have mu sub naught over 4 pi. I'll take the first version. dq times dx dt cross r over r cubed. We're not done then. But wait, there's more. I've got a fraction here, dx over dt. I can just shift that dt over, so I've got mu sub naught over 4 pi dq dt times dx cross r over r cubed. And what is dq dt? That's a 252 thing.
Current?
Yes, that's correct. So that's mu naught over 4 pi times the current dx cross r over r cubed. And that's the third form. In the fourth form, we do something very similar to what we did over there, or pretty much the identical thing to what we did over there. Mu naught over 4 pi I dx cross r hat over r squared. So we've got four forms of the exact same thing. One, so they're not independent of each other. So if you think about this in your physics career, we had F equals ma. We have the gravitational force is big G m1 m2 over r squared, and Hooke's law. We are now up to 5, plus the 2 from this course, 5 physics equations. All the rest is just math and definitions. And again, I know what you're thinking. Hey, this is great, but for the sake of the other people in the room, how would you actually use this? So let's actually use it. I'm gonna have a current floating off to the right, some current I. I'm gonna make this distance here, I'll make it big R. I want to figure out if I have a current going off to the right, as I've drawn on the diagram, what is the magnetic field at a point that is a distance R away? Well, as with any of these problems, I'm going to be using, it's one of the current formulas, I'm going to be using this form right here. So I need to define dx. I have to create my differential. So I'm going to create my differential right here. I'm going to say I got this dx right there. I'm going to make this line infinitely long, just because it's easier. So we need to define some stuff that I'm going to make this x is equal to 0 right there. That distance right there would be little r. This distance right here would be negative x. Actually, the distance is x. This point right here would be negative x. So I have a right triangle. Tell me the relationship between the sides of the right triangle.
X squared plus capital R squared equals little r squared.
That will come back. So I'm now plugging into my equation. So R is a vector from dx to this point in question. Why don't we just call it point P? So from dx to P, my R vector is a vector in that direction. So R vector is equal to, well, let's establish some coordinate system here. I hat and j hat. Given I hat and j hat, k hat has to be out of the board in a right-handed coordinate system. I cross j is k. So what is r hat? Sorry, not r hat. What is r? Given the notation I have set up here. I'm going from this point to this point. How far am I going to the right?
X. And R up, RJ, big RJ.
So now, let's do a little plug and chug over there. So I know that the differential of my magnetic field is equal to mu naught over 4 pi times my current times dx cross, so dx is in the I hat direction, so this is dx I hat cross x I hat plus big R j hat over r cubed. So it gives me mu naught over 4 pi I. All right. So dx I hat cross x I hat plus rj hat. What is that? Probably doesn't help that I'm using x's and crosses, but let me make my x's a little bit fancier here. So I got a cross product. What's I hat cross I hat?
Zero, right?
0. Cross products care about perpendicular. All right, so I hat cross I hat is 0, what's I hat cross j hat?
K hat.
So I end up with d big R dx k hat over r cubed. Well, I know what r squared is, so this would be x squared plus big R squared to the 3/2. All that's well and good, but I know what you're thinking. It'd be really nice if we could do some calculus. Your thought is my command. This time. So, I know that they integrate both sides. Technically, there it is. So my magnetic field is equal to, well, let's pull the constants out. I got mu naught I big R over 4 pi integral, oh, there's another constant I left out, k hat, integral dx over x squared plus big R squared to the 3/2. I now have it in terms of a single variable. I can establish my limits of integration. And what are the limits of integration?
Negative infinity to infinity.
Yep. And now we have to figure out what is the integral of dx over x squared plus r squared to the 3/2. BJ, you got that?
Yeah, it's, x over r squared, square root of r squared plus x squared. It's over that, that's still in the denominator, it's x over all of that.
X, okay.
So x over r squared times the square root of r squared plus x squared.
Well, that r squared is going to cancel out with one of the r's. Well, that r will cancel out with one of the r's, r squared, and there we go. So that cancels out with one of those. And so I'm left with mu naught I over 4 pi r times infinity over infinity minus negative infinity over infinity. And what is infinity over infinity minus negative infinity over infinity? 2. So that 2 is going to cancel out with one of those right there. And so what I am left with is the magnetic field at a distance big R away from a current is mu naught I over 2 pi r. I don't have the vector symbols in here because, well, specifically in this case, so in this situation, the magnetic field at point P would be k hat, but there is a right-hand rule involved here. If I have a charge moving or if I have a current going in a particular direction, just think about it. If you're hitchhiking, you hitchhike and you stick your thumb out. So you stick your thumb in the direction that you want to go or that the current charges are going, positive charges are going. Fingers curl in the direction of the magnetic field. So if the positive charges are going this way or negative charges going that way, if I have a current flowing this way, then my magnetic field above is out of the board, below is into the board. In the classroom space, it's going down, and in the hallway, it's going up. It's traveling in a circle. And there just happens to be a circumference of a circle right there. There's another formula that probably, well, we'll get to it. Questions to hear? Let's take this one step further, of course. I'm gonna multiply both sides by that circumference. Let's just drop the vector symbols for now. That's 2 pi r is equal to mu naught I. So that just be the magnetic field times this circle, times all along the circle. It's basically, it's a line integral. It's b times this length of this path. And I'm gonna make it slightly more generalized. This is obviously not a proof, this is taking a specific case and sort of working backwards. But if I have a circle here, and I have a line, current running through it, this would be the enclosed or encircled line. Just do encircled. And this is Ampere's law. Ampere, or however it's pronounced. Law d'Ampere, or d'Ampere.
So is that just Gauss's law for magnetic fields?
No. All right, so let's talk about Gauss's law of magnetic fields, because I probably should have hit that one a little bit sooner. If we look at Gauss's law of electricity, well, actually, let me quiz you. What is Gauss's law of electricity?
Q enclosed over epsilon sigma.
Equals,
Is it AE over? AE over Q?
no, we gotta do it on the right-hand side. What's A
Or
times
just
E?
AE,
What is A times E?
the area vector dotted with the electric field vector?
Which is also, what is the electric field times the area? It's a two-word answer. The first word is electric,
Potential. Electric potential.
not potential,
Flux?
flux. Yeah. So the integral of E dot dA. And I put a circle there because it's around it has to be enclosed. It has to be the surface it's a closed surface. All right, so this is Gauss's law of electricity. We can have this because we can have a charge by itself. A positive charge does not mean there's a negative charge hanging out nearby. However, with magnetic fields, if I got a north, I got a south. If I have my surface here, I have just as many field lines coming in as going out. So Gauss's law of magnetism, we look at the magnetic flux, and that's equal to 0. So Gauss's law of electricity, Gauss's law of magnetism, Ampere's law. Let's take to the next step. Oh, this goes back to something Benjamin said earlier about charge. If a monopole can exist, then it won't be equal to 0 anymore. So if a monopole can exist, and I think the symbol that I saw used was an M, but it could be something else. So M enclosed over mu sub naught. So if they ever find a monopole, then now they have a reason to have a magnetic charge, then it would be equal to this instead of 0.
What would finding a monopole change? Like, what can you do with that?
such an engineer. The answer to that will come in the next chapter. It won't be an answer that will be satisfying to you, but, oh, what the heck, I'll give it to you now. When Faraday, I've heard it attributed to a couple different physicists, but Faraday's the one I'm sticking with right here for this. When he found how to create a current from a magnetic field, he was telling reporters, the science reporters, telling reporters about this, and somebody asked, of what use is this? And his response is, of what use is a newborn child? So, he didn't know what use it would be, but he thought that it could grow into something incredible. And it turned out it did. Now, if we find a monopole, it'd probably be one of those things as close as physicists get to what I would refer to as physics porn. It is, yeah, it would just excite the physics world. Now, are there any practical applications? But whoever finds it, or the team that finds it, will, as a team, will be millionaires. I don't know what the Nobel endowment's up to now. Yeah, I wish I had a more practical answer to it, but from this group or the other group, it talked about how long it takes between the math to become useful and physics to become useful. In grad school, we figured out that it takes about 500 years for new math to become useful, and it takes about 50 years for new physics to become useful.
Are you gonna try and find that?
The monopole?
Yeah.
No. No. There was a story I heard in grad school. It was funny at the time, not as funny now. But supposedly some grad students decided to prank their professor, and they faked data so that it looked like he found a magnetic monopole.